Hello, welcome to another module in this massive open online course. So, we are looking at a practical application of Jensens inequality in the context of a wireless communication scenario. In fact, to look at a comparison, correct, of a wireless communication system, the performance of a wireless communication system, a comparison of that with that of a conventional digital or a wireline communication system, alright. And what we have seen is that this relevant channel model for your wireless communication system is Hx plus n, the signal has power p, noise has power sigma square. Now, because of the fading channel coefficient, this H is your fading channel coefficient, or this H is the fading coefficient. What has happened is your SNR of the wireless channel, that is magnitude H square times P over sigma square, which is magnitude H square times gamma. Further, what we will do is that we will set the expected, the average value of this magnitude H square, we will set this equal to 1. What happens because of this, that is, if you look at the average SNR of the expected value, that is the mean or the average SNR of the wireless communication system, that will be expected value of magnitude H square times gamma, which is basically, well, gamma times expected value of magnitude H square, and we have seen that expected magnitude H square equal to 1. So, this is gamma, which is nothing but the SNR of your AWGN channel, or let us call it as the SNR of the your conventional, correct, or your wireline communication system. So, this is a fair comparison, alright. So, we are using the same average SNR for both. It is not the case that a wireless system has a much higher SNR than the conventional communication system, alright. So, to perform a fair comparison between these two systems, we are choosing, alright, we are setting the SNR, or we are choosing the channel coefficient is basically assumed to follow a random, assumed to follow a probability density function such that the average SNR for both these scenarios is the same. Now, if you look at the probability of bit error for a wireless communication system, so if you look at the bit error rate for the wireless communication system, this will be Q of square root of the SNR for the wireless communication system, we have already seen that, and which is nothing but Q of square root of magnitude H square times gamma. Okay. So, this is known as the bit error rate, the instantaneous bit error, the bit error rate, or this is your basically bit error rate or probability of bit error for a wireless communication system. For a wireless communication system. Okay. And now we want to look at this function. Now, we already seen what is Q of x. Remember, Q of x is the CCDF of the standard Gaussian random variable. So, that is given as x to infinity 1 over square root of 2 pi e raised to minus t square by 2 dt. And therefore, Q of square root of x. Now, let us look at this function Q of square root of x, that will be integral square root of x to infinity 1 over square root of 2 pi, okay, e raised to minus t square by 2 dt, simply replacing x by square root of x, correct. That gives me Q of square root of Q of square root of x. Now, therefore, now what we want to show is if we denote this Q of square root of x by f of x, so f of x equals Q of square root of x, which is integral square root of x to infinity 1 over 2 pi e raised to minus t square by 2 dt. We want to show that this function f of x, this is a convex function. Okay. We want to show that, and that is easy to show, all right. So, we already know that q of x is a convex function, we want to show that q of square root of x is also a convex function, okay. And that is easy to show. If you differentiate this df by dx, remember first derivative of the top limit, but top limit is infinity, it is the constant, derivative is 0, minus derivative of the bottom limit, derivative of if you differentiate square root of x, you get 1 over 2 square root of x, 1 over square root of 2 pi, which is a constant, times you have to substitute the lower limit in the integral, that is e raised to minus x by 2. And now d square f of x by dx square, that is simple to evaluate. First let us evaluate the derivative of 1 over square root of x. So, this is 1 over 2 square root of 2 pi times that will be 1 over the derivative of, well, so minus 1 over 2 square root of 2 pi, derivative of square root 1 over square root of x, that is half x to the power of 3 by 2, and there is a minus sign, times e raised to minus x by 2 minus 1 over again 2 square root of 2 pi 1 over square root of x times derivative of e raised to minus x by 2, which is minus half e raised to minus x by 2. And now, if you simplify this, you can see that this derivative is nothing but 1 over, you can simplify this, 1 over 4 square root of 2 pi 1 over x raised to the power of 3 by 2 into e raised to minus x over 2 plus 1 over, well, this is actually 1 over again 1 over 4 square root of 2 pi times 1 over 4 square root of 2 pi times square root of x 1 over 4 square root of 2 pi times square root of x e raised to minus x by 2. And essentially the important thing is here you can see that the second order derivative, that is greater than or equal to 0, implies that, and this is greater than or equal to 0 for x greater than or equal to 0. So, implies that d square f x by dx square is greater than or equal to 0, implies f of x equals q of square root of x, this is convex. Okay. So, that shows that this beta rate function q of square root of x is a convex function. Okay. So, we start with that. Okay. So, f of x, q of x is convex as well as q of square root of x. Now, we are demonstrating this for q of square root of x because that is relevant in this context. Now, what does the Jensens inequality tell us? Let us recollect the Jensens inequality that tells us that f of, well, f of expected value of x, any random variable, is less than or equal to expected value of f of x. Okay. Now, this implies that if you look at our function f of x equals q of square root of x, this implies that your expected value of q of square root of your SNR for the wireless channel, which is magnitude h square gamma, which is nothing but your expected value of f of x, where f of x is your magnitude h square into gamma. Expected value of f of x, or so expected value of f of x is greater than or equal to the is greater than or equal to f of expected function of the expected value of x. So, this is greater than or equal to the function of the expected value of magnitude h square gamma. And now you observe something interesting. If you recall, our expected value of magnitude h square gamma, that is basically nothing but expected value of magnitude h square gamma, this is equal to gamma, because expected value of magnitude h square equals 1. That is precisely the condition that we set, so that both these communication systems have the same SNR on the average. Okay. And what you can see is this is greater than or equal to f of magnitude h square, and this is gamma, which is equal to f of, now you can see this is greater than or equal to f of gamma, which is nothing but q of square root of gamma. Okay. So, this is the, now q of s square root of gamma, this is basically beta rate of conventional or your wire line system. Okay. And what is this? Remember, q of square root of h square magnitude h square gamma, this is the instantaneous beta rate of the wireless communication system, which implies that expected value of this is the average bit error rate of a wireless communication system. So, this basically implies that the average bit error rate, correct, this basically shows, you know, theoretically and rigorously, that the average bit error rate of a wireless communication system for the same average SNR, remember both these systems have the same average SNR, yet the average bit error rate of a wireless communication system is significantly higher. In fact, you will see in practice that it is significantly higher than that of a conventional or a digital wireless communication system. Okay. So, this tells us the interesting, in fact the very interesting, one of the fundamental results that underpins the entire study of wireless communication systems is that average BR of wireless of a wireless communication system is greater than average average bit error rate of a wire line, or you can also say that as a conventional communication system, a communication system in which there is a wire or a guided propagation medium, or a wired medium, or the wire medium between the transmitter and receiver. And in fact, in practice this is often greater, that is, it is significantly greater. It is not just greater, but the average bit error rate of a wireless communication system is significantly greater than that of a wireline communication system or a wired communication system, which implies that the wireless communication of a wireless communication in a wireless system is highly unreliable, because the probability of bit error is very high. So, this quality, so this communication is highly unreliable, implies communication is highly unreliable, which is basically bit error rate is very high. And why is this arising? That is important. Remember, this is arising, all of this is arising because what is the fundamental difference between the wire line and a wireless communication system? The fading nature of the wireless channel, the fading channel coefficient. So, all this is arising because of the random nature of the fading channel coefficient. Okay. So, this is arising because of the fading nature of the wireless channel coefficient. Arises because of the fading nature of the wireless channel. Therefore, fading has a significant impact on the nature and in fact the nature and the performance of communication. In fact, fading leads to a severe degradation in the performance of a wireless communication system. Okay. So, fading leads to a significant, that is the challenge in wireless communication. Okay. Fading implies or leads to a severe degradation in performance. So, fading is basically a challenge. Okay. So, this is a challenge and one has to therefore overcome or surmount this challenge, overcome this fading nature. And that is why we need technologies to overcome this fading nature, and one of the most important technologies to overcome the fading nature or this degradation that arises due to fading is termed as diversity. Diversity is basically where you have multiple received signals at the receiver and you combine these receivers to enhance the signal to noise power ratio as well as the reliability of wireless communication. This principle is known as diversity. For instance, in a multiple antenna system where you have multiple receive antennas, you receive multiple copies of the signal, combine these signal copies to enhance the performance of the wireless communication system. Okay. So, the whole this fundamental property of wireless communication, all right, leads to technologies that overcome the fading, an example of diversity is multiple antennas. What happens in a multiple antenna system? We have already seen schematically. You have the receiver, all right. So, you have from the transmitter you have multiple copies. So, these are your, so this is your receiver, this is your transmitter. So, you have these multiple copies, or basically it is also diversity. Diversity means several, right, that is the English meaning of the word diversity. And these multiple signal copies you combine to enhance the signal to noise power ratio as well as reliability. Hence, diversity is a key principle in a wireless communication system, and in fact, one of the key technologies. is a very important or you can also say technology innovation. Diversity is a very important technology innovation. Diversity is a very important technology innovation for wireless communication systems, all right, and at the root of all this is basically the fading nature of the wireless channel and the performance, the poor performance of the wireless communication system, the very high bit rate, which can in fact be demonstrated using the Jensens inequality, and therefore Jensens inequality has a lot of applications, especially to prove fundamental results like this. It can also be used in, as I have already noted, can also be used to derive and prove several results in the context of information theory. So that basically summarizes the Jensens inequality and also shows its application in a very interesting context, in the context of performance comparison of a wireless versus a conventional wired communication system. All right, so we'll stop here and continue in subsequent modules. Thank you very much.